Neutron stars float silently in the cosmic void. They are the skeletal remains left behind after a star's life ends. The final resting place of a massive star after its glorious burn. When a star with a mass exceeding 8 times that of the Sun exhausts its nuclear fuel, it can no longer resist its own immense gravitational pull. Its core collapses in an instant, while its outer layers are hurled into the cosmos in a violent supernova explosion. The dense core that remains is the neutron star, a cosmic tombstone, marking the spot where a star once existed, recording the instant of its final demise. Yet the laws of the universe are never simple binary oppositions. Within death often lies the seed of new life. Where endings are found, beginnings are hidden. The star's tombstone of death is simultaneously the birthplace of a new elemental forge. Under the extreme conditions of a neutron star, matter is compressed to the density of atomic nuclei. Electrons are forced into the nucleus, merging with protons to form neutrons. The entire star is composed almost entirely of densely packed neutrons. This extreme state of matter is one we can never replicate on Earth. It creates unique conditions for the synthesis of heavy elements in the universe. When a neutron star orbits another neutron star or a black hole, they create ripples in space-time. These are gravitational waves. Gravitational waves continuously drain energy from the system, causing their orbits to gradually decay. Ultimately, these two compact celestial bodies spiral inward and collide violently. This collision ranks among the most violent events in the universe. The energy released is sufficient to briefly illuminate an entire galaxy. During this extreme collision, vast quantities of neutrons are released, creating ideal conditions for rapid neutron capture processes. Atomic nuclei absorb large numbers of neutrons in an extremely short time, and then transform into heavier, stable elements through beta decay. This process is known as the R process. It is the primary cosmic source of heavy elements like gold, platinum, and uranium. Each such neutron star merger event forges precious metals equivalent to several Earth masses and scatters them into interstellar space. These newly synthesized heavy elements mix with interstellar gas and dust, becoming the raw material for the next generation of stars and planetary systems. Our solar system, formed within such a gas cloud rich in heavy elements. All the gold on Earth and the gold atoms in your jewelry can be traced back to cosmic dust, produced by a neutron star merger in ancient times. In this sense, neutron stars stand as both the tombstones of stellar death and the smithies of new elements. They perfectly embody the profound dialectic in the cosmos, between death and rebirth, destruction and creation. Without stellar death, there would be no formation of neutron stars. Without neutron star mergers, there would be no production of heavy elements. Without the enrichment of heavy elements, there would be no formation of rocky planets. Without the emergence of life, much less the birth of humanity, every heavy element atom within our bodies has undergone nuclear fusion within a star, or been forged in the violent merger of neutron stars. We are, in every sense, children of stardust, deeply connected to these most extreme objects in the cosmos. This realization links us to distant cosmic phenomena, making us aware that human civilization is not isolated in a corner of the universe. It makes us realize that human civilization does not exist in isolation in a corner of the cosmos, but is a natural outcome of cosmic evolution. When we gaze at the stars, we see not merely distant points of light, but our very origins, our roots, as laboratories of extreme physics in the universe. Neutron stars continually challenge and expand the boundaries of human understanding. Their immense density, allows us to explore the behavior of matter under extreme conditions. Their super-strong magnetic fields enables us to study the principles of magnetohydrodynamics and quantum electrodynamics. Their immense gravitational pull allows us to test general relativity and various gravitational theories. Through neutron star research, we not only understand stellar life cycles, but also deepen our grasp of fundamental matter structures and interactions. Every observation of pulsar rhythms, every detection of gravitational wave signals, each recorded nova explosion, contributes to piecing together a more complete cosmic picture. Neutron stars play a pivotal role in the grand cosmic cycle, linking stellar death to planetary birth, connecting the destruction of matter to the emergence of life. Within this vast cycle, there is no true ending, only transformation of form, no complete extinction, only eternal evolution. The death of a star provides the material for countless planets to be born. A violent collision creates the conditions for life to emerge. We live within this cycle. We are its products and its witnesses. When we gaze upon extreme celestial bodies like neutron stars, we are not only exploring the mysteries of the universe, but also reflecting on humanity's place within it. Our existence is so fleeting, our individuality is so insignificant, yet we can comprehend these grand processes, trace the history of the cosmos, and explore the laws of nature. This itself is a form of cosmic self-awareness. Neutron stars, as tombstones of stellar death, remind us that all tangible things will eventually dissipate. As forgers of new elements, they reveal to us the creative power born from destruction. This magnificent epic of life and death is the most fundamental law governing the cosmos. It teaches us to respect natural laws, to understand the way of change, and to appreciate the fleeting yet precious nature of existence. On the cosmic scale, death is not an end, but the beginning of transformation. Destruction is not disappearance, but the prelude to rebirth. Through their extreme existence, neutron stars reveal this profound truth to us. We humans, as part of the cosmos, follow the same law. Though our lives are fleeting, the cultures we create, the knowledge we accumulate, the civilizations we pass on, will all become threads in the cosmic tapestry of evolution. Just as the heavy elements scattered by neutron stars merge into new stellar systems, our thoughts and creations will also become part of the future universe. This is the philosophical insight neutron stars offer us. They invite us to view life and death, existence and extinction, to view life and death, existence and extinction, the individual and the collective. In this vast cosmos, all things are interconnected, mutually transforming, weaving together the magnificent tapestry of the universe. And the neutron star, this extreme celestial body in the cosmos, in its unique way, reveals to us this eternal truth. It is both an end and a beginning, both death and rebirth, both a tombstone and a cradle. Understanding this may help us better comprehend the cosmos and better understand ourselves. This is the ultimate cosmological significance of neutron stars. They bridge the microscopic and the macroscopic. They link the past and the future. They connect death and life. In this grand connection, each of us is a part of the universe, participating in this eternal cycle. This is our story with neutron stars, and the universe's dialogue with itself. This is the most terrifying celestial body in the universe, and the densest object known beyond black holes. It is the neutron star. If we could extract a sugar cube-sized piece of neutron star matter, its weight would equal that of an entire mountain range on Earth. Such density utterly defies our everyday understanding. Neutron stars are born from the violent deaths of massive stars. They are the core remnants left behind after a star's final cataclysmic explosion. A star far more massive than the Sun, in its final moments, cannot resist its own immense gravitational pull, and violently collapses inward. This collapse compresses its enormous mass into a sphere just 20 kilometers across, forming a neutron star. Imagine packing more mass than the entire Sun into a space the size of a city. The energy represented by this compression is devastating. Under such extreme pressure, conventional material structures are utterly destroyed. Atoms themselves cease to exist. Electrons are forced into atomic nuclei by immense pressure, combining with protons to form neutrons. The entire planet is essentially a giant atomic nucleus composed of neutrons. Hence the name neutron star. This extreme density endows neutron stars with a series of astonishing properties. Their gravity is powerful enough to bend light. If you could stand on its surface and look up, you might see the image of the back of your own head. Its surface ranks among the smoothest interfaces in the cosmos. Any minute irregularity is instantly smoothed by its immense gravity. Nuclei also possess the strongest magnetic fields in the universe, reaching intensities trillions of times greater than Earth's magnetic field. Such powerful fields can instantly magnetize or destroy any complex electronic device from vast distances. When a neutron star spins rapidly, it emits periodic electromagnetic beams from its magnetic poles, like a cosmic lighthouse. Such neutron stars are called pulsars. Their regular signals once led scientists to suspect they were signals from extraterrestrial civilizations. Neutron stars are not merely cosmic wonders. They are natural laboratories for extreme physics. Here, the states of matter are impossible to replicate on Earth. Studying neutron stars helps us understand how matter behaves under extreme conditions. Moreover, when two neutron stars orbit each other and eventually collide, they forge most of the universe's heavy elements, such as gold and platinum. The gold in your jewelry likely traces back to an ancient neutron star collision. Thus, we share a profound connection with these most extreme objects in the cosmos. Neutron stars represent both gravity's ultimate triumph and a pivotal link in the cosmic cycle of matter. They signify a star's demise, yet herald the birth of new elements and worlds. To grasp the mind-boggling density of neutron stars, we need a powerful mental tool, an intuitive metaphor bridging the known and the unknown. Now imagine our life-sustaining sun. Its diameter spans 1.39 million kilometers, large enough to hold 1.3 million Earths. This blazing plasma giant holds 99.86% of our solar system's total mass. Its immense gravity governs the orbits of 8 planets. Within its core, nuclear fusion reactions occur ceaselessly, converting millions of tons of matter into energy that sustains life throughout the solar system. Such a colossal entity exceeds the volume of our blue planet by millions of times. Now let us initiate the most extreme compression process in the universe. Imagine possessing an infinitely powerful press, whose force could overcome all natural forces sustaining the sun's structure. We begin compressing the sun. First, its immense volume rapidly shrinks under gravity. The originally diffuse, incandescent gas is violently compressed. The space between atoms is completely eliminated. Electrons are forced into atomic nuclei, fusing with protons to form neutrons. The endpoint of this process is compressing the sun's entire mass, approximately 200 billion tons of matter, into a sphere just 20 kilometers in diameter. What does 20 kilometers mean? It's roughly the diameter of a modern metropolis. Imagine driving from one end of the city to the other. Without traffic, it might take only 20 or 30 minutes. For example, the diameter of Beijing's Fifth Ring Road falls within this range. Now, picture this scene in your mind. A star once so magnificent and vast it illuminated the entire solar system has been compressed into a sphere that could easily fit within the central district of your city. This sphere has a volume equivalent to that of a city, yet it retains the entire mass of the sun. This analogy aims to give us an intuitive sense of extreme density. In physics, density is defined as mass divided by volume. When mass remains constant while volume shrinks dramatically, its density increases by astronomical factors. This is the defining characteristic of a neutron star. To grasp the extreme nature of this compression, consider a more relatable analogy. Imagine compressing all of humanity on Earth, over 8 billion people, into a space the size of a sugar cube. This tiny cube would possess the total mass of all humanity. Yet even this pales in comparison to the density of a neutron star, because neutron stars are several times denser than this hypothetical scenario. What immense force is required to achieve such compression? This force stems from one of the most fundamental and powerful forces in the universe, gravity. When nuclear fusion ceases in a star's core, no longer generating outward radiation pressure, gravity gains absolute dominance. Unopposed, it triggers catastrophic gravitational collapse. This gravitational force is so immense that it overpowers even the electromagnetic force holding atoms together. In ordinary matter, the interior of an atom is remarkably sparse. The nucleus sits like a grain of sand in the center of a vast stadium, while electrons race around the stands at high speed. But inside a neutron star, gravity demolishes this stadium. It forces all the electrons from the stands toward the central nucleus. This compression is so complete that atoms lose their fundamental identity. The entire planet transforms into a dense ocean composed primarily of neutrons. This state, sustained by neutron degenerate pressure, stands as the final defense against matter succumbing to gravity and collapsing into a black hole. Through this metaphor of compressing the sun to the size of a city, we not only intuitively grasp the staggering density of neutron stars, but also begin to comprehend the cosmic scale extreme conditions. This simple analogy opens a window, allowing us to glimpse a physical reality far beyond everyday experience, and lays a solid foundation for understanding the subsequent, even more peculiar properties of neutron stars. In the universe's relentless laws, death is never a pure ending. It often gives birth to incredible new life. The neutron star stands as the most extreme embodiment of this cosmic truth. It is not merely a pile of simple ashes at the end of a star's life, but the most magnificent and peculiar legacy, forged by a massive star in the fiery flames of its own destruction. When a star more than 8 times the mass of the sun enters its twilight years, it has exhausted the nuclear fuel sustaining its equilibrium. Its core no longer generates sufficient outward radiation pressure to counteract its immense inward gravitational pull. Thus, under gravity's absolute dominion, the stellar core undergoes the most violent collapse in the cosmos. This is no gentle contraction, but an instantaneous implosion occurring at 1/4 the speed of light. The gravitational potential energy unleashed by this collapse is unimaginable. It ignites the star's outer layers, igniting a cosmic fireworks display known as a supernova explosion. Supernova explosions rank among the most spectacular events in the cosmos. Their instantaneous burst of light can briefly outshine the entire host galaxy. In this violent explosion, the star's outer layers are hurled into interstellar space at immense speeds. This ejected material is rich in heavy elements and will become the raw material for future generations of stars, planets, and even life. Meanwhile, at the explosion's core, the inner nucleus gripped tightly by gravity, a completely different fate unfolds. The star's outer shell is blown apart, while its core rapidly collapses under its own gravity. This collapsing force is so immense, it crushes the original structure of matter. Under normal conditions, the interior of an atom is extremely sparse. Yet within the collapsing core, this structure is ruthlessly destroyed. Negatively charged electrons are violently forced into the atomic nucleus, where they combine with positively charged protons to form neutrons, while releasing nearly massless neutrinos. This process is known as neutronization. When the core's density reaches that of the atomic nucleus, a new force comes into play, that is neutron degeneracy pressure. This quantum mechanical effect prevents further compression of neutrons, offering the final resistance against gravitational collapse. If the core's mass does not exceed a critical threshold, roughly 3 times the mass of the Sun, degeneracy pressure can establish a new equilibrium with gravity. This collapsed core, having reached a new balance, is what we call a neutron star. Thus, the essence of a neutron star is the highly compressed, dense core, left behind after a massive star undergoes a supernova explosion. It is the skeletal remains of a star's death, yet these remains contain the concentrated essence of the star's entire lifetime. Mass equivalent to an entire sun, or even twice the sun's mass, is condensed into a sphere just 20 kilometers in diameter. This makes it the densest object in the universe, second only to black holes. The value of this legacy extends far beyond its astonishing density. Neutron stars provide us with a unique natural laboratory. Within this laboratory, matter exists under extreme conditions impossible to replicate on Earth. Temperatures reaching millions of degrees, magnetic fields trillions of times stronger than Earth's, densities that dwarf even those of white dwarfs. Studying neutron star behavior allows us to test the limits of physical laws under such extreme conditions. This has significantly advanced the development of gravitational physics, nuclear physics, and magnetohydrodynamics. Even more astonishingly, neutron stars play a pivotal role in the cosmic cycle of matter. When 2 neutron stars orbit each other under gravitational pull and eventually merge, they eject vast amounts of neutron-rich material. This material undergoes rapid neutron capture processes, known as the R process, into heavy elements like gold, silver, platinum, and uranium, virtually all elements heavier than iron found on Earth, including the gold jewelry you wear, likely trace back in significant part to ancient neutron star mergers. Thus, as stellar legacies, neutron stars connect not only the birth and death of stars, but directly link the chemical evolution of the universe, and even our own origins. They stand as both the tombstones of old stellar lives, and the cradles of new matter and new life. They reveal to us the profound and eternal connection between destruction and creation, between endings and beginnings in the cosmos. This legacy from stellar death is undoubtedly one of the most precious treasures for understanding the mysteries of the universe. The fate of every star is largely predetermined at its birth. The key to this destiny lies in the mass it possessed at formation. Stars of modest mass, like our Sun, meet a relatively peaceful end. They evolve into white dwarfs, gradually cooling and fading over vast spans of time. But for giants exceeding 8 times the Sun's mass, the conclusion is starkly different, filled with violent grandeur, and ultimately giving birth to one of the universe's most extraordinary objects, neutron stars. To understand how neutron stars emerge from stellar ruins, we must first grasp how stars live and die. A star is essentially a massive, gravitationally confined nuclear fusion reactor, where continuous nuclear fusion reactions occur within its core. This process generates immense outward radiation pressure. This outward pressure balances the powerful inward gravitational pull generated by the star's own mass, creating a delicate dynamic equilibrium. This balance sustains the star's macroscopic structural stability, allowing it to maintain relatively constant volume and luminosity for billions of years or longer. Yet the fuel required for nuclear fusion is not inexhaustible. A star's life is a race against its own gravity. It must continuously burn its internal nuclear fuel to generate sufficient force to counteract gravitational collapse. For massive stars, nuclear fusion occurs in distinct layers within their interiors, much like a cosmic onion. During the primary phase of its life, a star burns hydrogen in its core through either the proton-proton chain reaction or the carbon-nitrogen-oxygen cycle, fusing hydrogen into helium. This stage occupies the majority of a star's lifetime. Our Sun currently resides in this stable phase. When the core's hydrogen reserves are depleted, gravity temporarily gains the upper hand, causing the core to contract. This contraction rapidly increases temperature and pressure, igniting hydrogen fusion in the outer shell of the core. Simultaneously, the compressed core itself heats to temperatures sufficient to fuse helium into carbon and oxygen. For massive stars, this process progresses layer by layer. Each stage burns heavier elements and produces heavier elements as ashes. After hydrogen depletion, helium ignites to form carbon and oxygen. Then carbon burns to produce helium and magnesium. Oxygen combusts to yield silicon and sulfur. Finally, silicon undergoes fusion to ultimately form iron. The emergence of iron signals the death knell for the star, as iron possesses the highest average binding energy among atomic nuclei. This means that whether converting iron into heavier elements through fusion, or breaking it down into lighter elements through fission, requires absorbing energy from the outside, rather than releasing it. For a star, iron is like ashes that cannot be further utilized after combustion. It accumulates in the star's core, and no longer participates in energy-producing nuclear fusion reactions. Consequently, it can no longer generate outward radiation pressure to support the immense weight of the star's outer layers. At this point, the stellar core resembles an engine on the verge of shutting down. Its once glorious nuclear fire gradually fades, while the immense mass of the outer layers remains undiminished. Under the relentless pull of gravity, continues to compress the core without mercy. The exquisite equilibrium within the star, maintained for millions or even billions of years, is utterly shattered. Gravity, having lost its final counterbalance, sets in motion the most violent catastrophic collapse. In the cosmos, an event now unavoidable, this iron core, becomes the direct stage for the star's death and the birth of a neutron star. When the core of a massive star becomes an iron core that no longer releases energy, the collapse of its internal support structure is instantaneous and catastrophic. Deprived of outward radiation pressure support, the star's immense outer mass, under the influence of gravity, like an elevator with its cables snapped, begins free-falling toward the core. This gravitational collapse initially occurs within the iron core. At unimaginable speeds, core material plummets inward, at speeds reaching 70,000 kilometers per second, equivalent to 1/4 the speed of light. Such extreme collapse means a stellar core originally Earth-sized collapses in a fraction of a second in physical terms. During the initial collapse phase, extreme conditions emerge, with core density and temperature skyrocketing. When density surpasses 10 million grams per cubic centimeter, peculiar quantum effect takes hold. Electrons within the core material are forcibly squeezed into protons within atomic nuclei by immense pressure. This process is called electron capture, where an electron and a proton combine to form a neutron, while releasing a neutrino. This reaction has a dual destructive impact. First, it removes a portion of the electrons that provide support pressure within the core. These electrons originally played a crucial role in resisting gravitational collapse through electron degeneracy pressure. Second, the neutrinos produced initially interact strongly with matter. However, as density increases further, they eventually escape the core almost unimpeded, carrying away the enormous energy released by the core's collapse. This further weakens the core's support, accelerating its collapse. The core's collapse continues until its density reaches or exceeds that of atomic nuclei, approximately 300 million tons per cubic centimeter. At this density, the state of matter undergoes a fundamental transformation. Between neutrons tightly compressed together, a new, powerful quantum pressure emerges, known as neutron degeneracy pressure. This pressure stems from the Pauli exclusion principle, which prohibits two identical fermions, such as neutrons, from occupying the same quantum state. When matter is compressed to such extreme levels, the low-energy quantum states available for neutrons to occupy become fully filled. Any further compression must force neutrons into higher energy states, requiring enormous energy input, thereby generating a powerful outward degeneracy pressure. When the core density reaches atomic nucleus density, this newly formed neutron degeneracy pressure acts as an invisible shockwave, violently resisting and attempting to halt further gravitational compression. For a core destined to form a neutron star, its mass falls just below the critical threshold for black hole formation, roughly 3 solar masses, allowing neutron degeneracy pressure to ultimately counterbalance gravity. This millisecond-scale struggle abruptly halts the core's collapse, causing the core matter to violently rebound, like a spring compressed to its limit suddenly released. This rebound effect of the core material collides catastrophically with the outer layers, still plummeting inward at high velocity, generating an extremely powerful shockwave propagating outward. Initially, this shockwave may stall due to energy dissipation, but a small fraction of the energy carried away by neutrinos is sufficient to reignite it. When this shockwave pierced the star's outer layers, it manifested as an extraordinarily bright supernova explosion. This explosion hurled most of the star's mass back into interstellar space. At the very epicenter of the explosion, the fiery, dense remnant core that had endured hellish collapse and was now propped up by neutron degenerate pressure became a newborn neutron star. It embodies the star's final dignity, becoming an immortal legacy left at the moment of its death. When the stellar core collapses and abruptly halts, forming the newborn neutron star, the grandest fireworks display in the cosmos has only just begun. The powerful shockwave generated by the core's rebound propagates outward at extreme velocity, violently colliding with the outer stellar material, plunging inward at nearly a quarter of the speed of light. This energy is so immense that it instantly reignites the halted nuclear fusion reaction. As the shockwave passes through, it forges nearly all known chemical elements from iron to uranium. These newly formed substances are hurled into interstellar space at tremendous velocity by the explosion. This is the Type II supernova explosion we observe. The scale of energy released transcends the limits of human language. At the peak of the explosion, The light emitted by this single star equals the combined radiance of hundreds of billions of stars in its entire galaxy. Its brightness could even briefly illuminate its entire galaxy cluster. In some corner of the cosmos, a faint galaxy that might otherwise require a telescope to glimpse suddenly blazes like the moon in the night sky as one of its stars meets its end. The light emitted by a supernova explosion represents only a minuscule fraction of its total energy release. This explosion propels stellar material, several times the mass of the Sun, into the vastness of interstellar space at speeds approaching 1/10 the speed of light. This ejected material is rich in heavy elements like oxygen, silicon, and iron, as well as heavier elements such as gold and uranium. Acting like cosmic cedars, they provide the essential raw materials for the formation of future generations of stars, planets, and even life. Every atom in our bodies, except for the lightest hydrogen, originated from some ancient supernova explosion. We are truly children of stardust. After the electromagnetic radiation from the explosion gradually fades, the expanding supernova remnant persists in interstellar space for tens of thousands of years. Interacting with the interstellar medium, it forms beautiful nebulae stretching dozens of light years. Supernova remnants like the Crab Nebula continue to expand outward at high speeds. At its core beats the heart of a pulsar, recorded by ancient Chinese astronomers in 1054. This cosmic fireworks display is not merely a stellar funeral rite, but a force of creation. It shatters the gravitational cage within the star, returning the heavy elements forged through a lifetime of nuclear fusion back to the cosmos, infusing new vitality into the universe's chemical evolution. Without supernova explosions, the universe would contain only hydrogen and helium. No rocky planets would exist, no complex organic molecules capable of nurturing life, nor would humanity exist. Thus, each such explosion, though signifying a star's demise, also heralds the dawn of countless new worlds and possibilities, as the shockwave of a supernova carries the star's outer layers, rushing into interstellar space. At the explosion's epicenter, an extreme compression unfolds. The core, having endured catastrophic collapse and sustained by neutron degenerate pressure, completes its final transformation into a neutron star. The temperature of a newly formed neutron star is extremely high, possibly exceeding 100 million billion degrees Celsius. Yet from this moment on, its destiny is governed jointly by gravity and quantum mechanics. Its internal structure is largely determined the instant it forms, a complete revolution in the state of matter. The internal structure of a neutron star can be imagined as a cosmic onion, with the outermost layer being an extremely strong iron shell, where iron nuclei are compressed into a tightly packed crystalline lattice by immense pressure. Its density, starting at roughly 10,000 grams per cubic centimeter at the surface, increases rapidly with depth. Just 1 kilometer below the surface, density may soar to 1 billion grams per cubic centimeter, millions of times denser than any material on Earth. Beneath this hard crust, we enter the neutron star's truly bizarre core. Here, the pressure is so immense that individual atomic nuclei can no longer maintain their independent existence. The distances between nuclei vanish, and they fuse together to form an ocean composed primarily of neutrons, with a small admixture of protons and electrons. This is the so-called inner core. As depth increases further, pressure continues to rise, and the state of matter begins to grow even more peculiar. Below a certain critical point, neutrons, these fermions, begin to exhibit superfluid properties. A superfluid is a peculiar state of matter manifested macroscopically through quantum effects. It possesses zero viscosity and zero friction, enabling perpetual flow without resistance. The superfluid neutrons within a neutron star can form microscopic vortices through rotation. These vortex arrays may interact with the star's intense magnetic field, influencing surface activity and even rotational changes. As for the deepest core of a neutron star, where density may exceed that of atomic nuclei by several orders of magnitude, physicists know little about the state of matter there, relying solely on theoretical speculation. Under such extreme pressure, neutrons themselves may be crushed, decomposed into their more fundamental building blocks, quarks. These up and down quarks might freely roam, forming what is termed quark soup or quark matter, or even exotic S-quarks, composing an entirely new form of matter, strange matter. Another intriguing theoretical hypothesis suggests that at such immense densities, nucleons might be stretched into bizarre shapes, vividly dubbed nucleon spaghetti by physicists, ranging from flat lasagna-like layers to slender spaghetti-like strands. These structures are considered the strongest materials in the universe. It is precisely these layered structures, from crust to core, that collectively support and define a complete neutron star. No longer the star that once burned, but a brand new, densely packed marvel, forged from the most extreme physical forces in the universe, upon the ruins of its death. To truly grasp the awe-inspiring density of a neutron star, we need a metaphor closer to home. Let us withdraw our gaze from the distant depths of the cosmos. Focus instead on the blue planet we call home, Earth. Earth's diameter spans approximately 12,700 kilometers. Its mass approaches 600 trillion tons. It possesses a crust composed of rock, a mantle formed of molten rock, and a massive core made of iron and nickel. This complex and diverse structure supports vast oceans, towering mountains, and all life we know. Now, in our imagination, let us activate a cosmic compressor to simulate the extreme physical processes forming neutron stars. Applied to our Earth, this compression process means we must overcome all chemical bonds and electromagnetic forces that maintain Earth's structure, completely crushing every atom that constitutes it. First, Earth's macroscopic structure would vanish instantly. All mountains, oceans, and basins would cease to exist. Under overwhelming force, Earth begins to shrink dramatically. The fundamental particles composing matter would be forcibly compressed together. The vast empty space surrounding atomic nuclei would be completely eliminated. Electrons would be squeezed into the nucleus, combining with protons to form neutrons. When all of Earth's mass is compressed to its final stage of resisting gravity, that is, when neutron degenerate pressure sustains the entire structure, what we would obtain would no longer be the world we know. Instead, it would be a perfect sphere with a diameter of only about 200 meters. This size is equivalent to the length of a large stadium, or the area of a small city block. You could easily walk around its circumference in minutes. Yet this tiny sphere retains the entire mass of the Earth. 60 trillion tons of matter are locked within this minuscule space, representing the ultimate expression of density. Its density reaches hundreds of millions of tons per cubic centimeter, a figure utterly beyond human sensory experience. To grasp this more concretely, imagine taking a piece of matter, the size of a sugar cube from this compressed Earth sphere. This seemingly insignificant fragment would weigh hundreds of millions of tons, equivalent to many times the combined weight of all humanity, or the mass of a massive mountain like Mount Everest. This means you'd need every ship and truck on Earth just to barely drag this tiny sugar cube. This extreme density stems from a fundamental transformation of matter's structure. In normal matter, the interior of atoms is vast and empty. The nucleus occupies only 1/1,000,000th of the atom's total volume. The remainder is a void of space where electrons move. But within neutron star matter, this spacious structure is ruthlessly shattered by gravity. Atomic nuclei are pressed tightly together. The electromagnetic repulsion between them is completely overwhelmed by immense gravitational force. Electrons are forced into the nuclei, forming matter composed almost entirely of neutrons. Neutrons press tightly against one another, their spacing compressed to dimensions comparable to the neutrons themselves. The entire planet resembles a gigantic atomic nucleus, naturally attaining a density on the scale of an atomic nucleus. This is why a neutron star can compress a mass as large as Earth's into a volume the size of a sports stadium. Understanding this extreme density is the first key to unlocking all the marvelous and terrifying properties of neutron stars. It directly leads to the next, even more bizarre effect, the warping of spacetime itself. According to Einstein's general theory of relativity, matter and energy dictate how spacetime bends, and this warped spacetime dictates how matter moves. The gravity we perceive is fundamentally the effect of spacetime curvature. The greater a celestial body's mass and density, the more intensely it warps the surrounding spacetime. The neutron star is such a perfect warper of spacetime. It concentrates immense mass into an extremely small volume, thereby creating one of the strongest gravitational fields in the universe around itself, second only to black holes. This extreme gravitational field exerts an incredible influence on light. Light always travels along the shortest path in spacetime, known as a geodesic. In flat spacetime, this typically manifests as a straight line. But around a neutron star, where spacetime is severely warped by mass, the path of light undergoes significant deflection. This phenomenon is known as the gravitational lensing effect. Imagine you are a brave astronaut, standing on the incredibly smooth surface of a neutron star. Due to the extreme curvature of spacetime, the trajectory of light is profoundly distorted. When you attempt to gaze straight ahead at the starry sky, what you see will not be the familiar cosmic panorama, but a distorted, chaotic, yet strikingly beautiful and peculiar scene. Light rays from different directions will curve around the warped spacetime and converge into your eyes from all angles. The effect is that you will be able to see celestial bodies located to your side or even behind you. Theoretically, if your eyes were sensitive enough, and the neutron star's gravity sufficiently intense, you might even see the back of your own head, because light reflected from your occipital region would circle the neutron star once, before precisely returning to enter your own pupils. This is not magic, but a direct consequence of general relativity. Gravity's influence on light extends beyond this bizarre visual phenomenon. It also induces gravitational time dilation. On the surface of a neutron star, gravity is so intense that time flows noticeably slower than in the surrounding cosmic space. If you placed a clock on the neutron star's surface and observed it through a telescope from afar, you'd see its hands moving extremely slowly. Each heartbeat, each breath you take, would appear stretched into slow motion to a distant observer. This means that if you could remain on this stellar body for a period, upon returning to normal space-time, you would find that far more time has elapsed externally than you personally experienced. This effect is real and has been verified by modern technology. For instance, the global positioning system we use daily must account for the minute time dilation caused by Earth's gravity. Otherwise, positioning accuracy would rapidly deteriorate. The time dilation effect on a neutron star is 1 trillion times stronger than on Earth. The neutron star's powerful gravitational field also acts as a cosmic magnifying glass. When light from a background star passes near the neutron star, its path is bent and focused. Under the influence of the neutron star's gravitational field, this background star appears exceptionally bright. This phenomenon provides astronomers with a powerful tool to indirectly detect neutron stars and even measure their mass. Understanding the extremely distorted spacetime around neutron stars not only reveals the wonders of the cosmos, but also profoundly reminds us that our universe is not a rigid stage, but a dynamic, flexible structure, where the distribution of matter determines its shape, and its shape in turn dictates the motion of matter. Neutron stars, in their extreme form, present gravity's most spectacular performance, serving as one of the most perfect natural laboratories for testing Einstein's great theory. One of the most perplexing and captivating features of neutron stars lies in the extreme mismatch between their mass and size. A typical neutron star has a diameter of about 20 kilometers. This scale is small enough to fit within a medium-sized city. You could easily drive around it in half an hour. Yet within this minuscule spatial range, contains a total mass equivalent to 1.4 to 2.1 times that of the Sun. To grasp how extreme this contrast is, let us revisit our Sun. The Sun's diameter reaches 1.39 million kilometers, 109 times that of Earth's. Its mass dominates the entire solar system, yet a neutron star, with a volume merely 1/10,000th of the Sun's or even smaller, carries a mass comparable to or even greater than the Sun's. This extreme concentration of mass gives rise to some of the most peculiar consequences in physics. The mass of a neutron star has clear upper and lower limits. The upper limit is known as the Oppenheimer limit, roughly 3 times the mass of the Sun. If the core mass remaining after a star's collapse exceeds this limit, even neutron degeneracy pressure cannot resist gravity. The core will continue collapsing into a black hole, vanishing forever beyond the event horizon. The lower mass limit is approximately 1/10 of a solar mass. Below this mass, gravity becomes insufficient to compress atoms into neutron matter, resulting instead in a white dwarf. Neutron stars occupy precisely the narrow mass window between these two limits. This makes them exceptionally unique stellar remnants. Why do neutron stars maintain such a consistent size of around 20 kilometers? This stems from a profound physical principle. Neutron stars are supported by neutron degeneracy pressure. Degeneracy pressure is a quantum mechanical effect that does not depend on temperature. This means that whether a neutron star is newly born and fiercely hot, or aged and cold, once its mass is determined, its radius is also largely fixed. When a neutron star increases its mass through processes like accretion, a counterintuitive phenomenon occurs. It actually contracts to a smaller size. This is because greater mass generates stronger gravity, requiring higher density and smaller volume to produce stronger degenerate pressure to counteract it. This process continues until the mass breaches the upper limit, leading to complete collapse into a black hole. The mass and size of neutron stars are not fixed values, but rather fall within a distribution range. This depends on multiple factors, including the mass of its progenitor star, its own rotational speed, and the internal state of its matter. However, a diameter around 20 kilometers and 1 to 2 solar masses represent the most typical and representative values. Understanding this extreme mass-size relationship is the cornerstone for comprehending all the extreme properties of neutron stars. It directly explains why neutron stars possess one of the strongest gravitational fields in the universe, and why they serve as natural laboratories for testing fundamental physical theories. this tiny giant of the cosmos, speaks to us through its very existence, of the immense power of gravity and the peculiarities of the quantum world. The immense mass concentrated within a tiny space endows neutron stars with a terrifying characteristic, one of the strongest surface gravities in the universe. The gravitational acceleration at their surface can reach 100 billion times that of Earth's gravity. This figure lies entirely beyond the scope of human survival experience. In such an extreme gravitational environment, any object attempting to land on its surface, be it a sturdy spacecraft or any form of material mass, will meet an instant and complete annihilation. This destructive force primarily stems from an effect known as tidal forces. Tidal forces essentially arise from variations in gravitational field strength. When an object approaches a massive celestial body, the gravitational pull on the side closest to the body far exceeds that on the side farther away. This gravitational disparity generates a powerful stretching force that attempts to elongate and tear the object apart. We can observe faint manifestations of tidal forces on Earth. The Moon's gravity causes Earth's oceans to bulge toward and away from the Moon, forming the familiar tidal phenomenon. But for neutron stars, this effect is amplified to its extreme. A classic analogy is, if you were to dangle like a rope toward a neutron star, the gravitational pull on your feet would far exceed that on your head. This force difference would instantly stretch you into a long, thin stream of atoms. This process has a vivid name in physics: spaghettification. Any object falling toward a neutron star will first be torn apart by these immense tidal forces into fundamental particles. Even these particles will, upon impact with the surface, be converted into a beam of high-energy X-rays or gamma rays, releasing enormous amounts of energy. This annihilation occurs beyond a boundary known as the tidal disruption radius, long before the object actually touches the neutron star's surface. For a typical neutron star, this safety boundary may lie hundreds of kilometers above its surface. Once crossed, no known material structure can remain intact. The neutron star's immense gravity not only destroys macroscopic objects, but can even significantly alter the existence of its companion star. In a binary system, if a neutron star has a normal star as its companion, its immense gravity acts like a cosmic pump, continuously stripping material from the companion's surface via the Lagrange points. This stripped gas does not fall directly onto the neutron star, but instead forms an accretion disk orbiting the neutron star. Within the disk, matter spirals inward. Friction heats it to millions of degrees, emitting intense X-ray radiation. Such celestial bodies are known as X-ray binaries and represent major X-ray sources in the cosmos. In this process, what is actually consumed is the companion star's stellar material, specifically hydrogen and helium elements. As they plummet toward the neutron star, they are heated and torn apart, ultimately either impacting the surface to release energy or guided along the neutron star's powerful magnetic field lines toward its poles, forming localized hotspots. With its nearly invincible surface gravity, the neutron star carves out an absolute forbidden zone in the cosmos. Any material approaching it signifies the end of its physical structure and the ultimate conversion of energy. It resembles a cosmic tyrant, proclaiming absolute dominion over surrounding spacetime with its unchallenged gravitational authority. If we could peel back the neutron star's mysterious outer layer and venture deep into its interior for a fantastical expedition, our first stop would be its extraordinarily peculiar crust, radically different from Earth's silicate rock crust. The neutron star's crust is a crystalline structure composed of extremely dense iron atomic nuclei. The hardness of this crust surpasses any known natural material in the universe. Its strength exceeds that of Earth's hardest steel by over 10 billion times. The neutron star's crust is not a uniform entity. It can itself be roughly divided into inner and outer layers. The outer crust primarily consists of relatively stable atomic nuclei like iron, silicon, and nickel. Under immense pressure, these nuclei are compressed into an extremely regular crystal lattice structure, resembling an incredibly robust cosmic metallic crystal. Yet even this relatively conventional layer reaches a density of approximately 10,000 kilograms per cubic centimeter. This is equivalent to compressing the mass of an entire aircraft carrier into a volume the size of a sugar cube, and this is merely the outermost layer of the neutron star's crust. As we delve deeper into the crust, pressure and density escalate at an astonishing rate. By the time we reach a depth of 1 kilometer below the surface, the environment has undergone a radical transformation. Here, the pressure becomes so immense it begins to distort the very form of atomic nuclei. This marks the beginning of the inner crust. In this region, traditional spherical atomic nuclei cannot remain stable. They are stretched and compressed by immense pressure, deforming into bizarre shapes that physicists vividly describe as nuclear pasta. These forms include flat, layered structures and elongated, cylindrical, noodle-like structures. These bizarre atomic structures are considered the densest matter in the universe. They form the skeletal framework of neutron star crusts, endowing the crust with incredible mechanical strength. When the crust experiences stress, such as from the star's rotational deceleration or the drag of internal superfluid vortices, these nuclear pasta structures resist deformation until stress accumulates to a critical point, at which point the entire crustal structure may undergo sudden global fracturing. This phenomenon is known as a starquake. The energy released by a single starquake is sufficient to instantly alter the entire neutron star's rotation period and trigger violent reorganization of its magnetosphere, emitting powerful X-ray and gamma-ray bursts from the surface down to the crust core boundary. The density increases dramatically from 10,000 kilograms per cubic centimeter to nearly the nuclear density of 400 trillion kilograms per cubic centimeter. This boundary typically lies about 1 kilometer below the surface. Despite the crust's thickness of only 1 kilometer, its mass may equal that of the entire Earth. This extreme state of matter is impossible to replicate on Earth. It provides a unique natural laboratory for studying the properties of matter under extreme densities. Understanding the crustal structure of neutron stars is crucial, as it not only determines the star's overall mechanical properties, but also relates to the generation and evolution of its magnetic field and various observed explosive phenomena. This seemingly thin iron shell serves as the first barrier protecting the even more bizarre world within. Penetrating this incredibly hard and densely packed iron crust leads us into the even stranger realms within the neutron star. Here lies a vast, superfluid ocean composed entirely of neutrons. None of the familiar states, solid, liquid, or gas, exist here. Matter persists in a purely quantum mechanical form, exhibiting astonishing properties. Superfluidity represents a peculiar state of matter manifested at the quantum macroscopic level. Possesses zero viscosity, meaning it can flow perpetually without friction. The closest terrestrial example is liquid helium forming a superfluid at cryogenic temperatures. Can climb container walls and drip downward, penetrate gaps too narrow for even gases to pass. Yet, the neutron superfluid within neutron stars amplifies this property to cosmic scale. This ocean of neutron superfluid extends kilometers deep, Its density increases from 400 trillion kilograms per cubic centimeter at the crustal boundary to staggering values at the core's edge. Within this ocean, individual neutrons lose their distinct identity, operating at extremely low temperatures. Though still hundreds of thousands of kelvins, they reach temperatures minuscule relative to their Fermi energy. They coalesce into a vast quantum system, where all neutrons condense into the lowest energy quantum state, moving in perfect unison. This state bears striking physical parallels to the behavior of photons in lasers, or electron-Couperin pairs in superconductors. This superfluid ocean is far from inert. It possesses complex and active internal dynamics. Due to the star's rotation, this superfluid generates numerous microscopic vortices. At the core of each vortex lies a quantized circulation. These vortex lines resemble the universe's tiniest tornadoes, are neatly arranged within the star's interior. Their existence and motion are closely linked to many observed characteristics of the star. For instance, when a neutron star undergoes a starquake, and its crust fractures and realigns, its rotational speed suddenly accelerates. Subsequently, the star gradually returns to its pre-quake rotation rate. This phenomenon is known as a spin-flip event, and its underlying physical mechanism is believed to be related to the internal neutron superfluid. When the crust abruptly changes its rotational speed due to a starquake, the frictionless superfluid within initially maintains its original rotational velocity. Subsequently, through interactions with its internal vortices, the superfluid's angular momentum is gradually transferred to the crust, allowing its rotational speed to slowly recover. This ocean of superfluid is also linked to another mystery of neutron stars, namely the origin and maintenance of their magnetic fields. While mainstream theories suggest neutron stars inherit their intense magnetic fields from progenitor stars, which are compressed and amplified, theoretical models suggest the convective motion within this superfluid may function like a cosmic dynamo, capable of sustaining or even generating the star's immense magnetic field over long periods. This vast ocean of neutron superfluid serves as an intermediate realm bridging the solid crust and the even stranger core. It possesses neither the fixed shape of the crust, nor the profoundly unknown nature of a potential quark core. It exists as a fluid, frictionless quantum liquid, perfectly demonstrating how quantum mechanics governs macroscopic physical processes. Under extreme densities, understanding it represents not only a frontier challenge in physics, but also a crucial step toward unraveling neutron stars' many mysteries. In the final chapter of our neutron star interior exploration, we shall reach its most enigmatic region, the core. Situated at the very heart of the stellar body, pressure and density reach the ultimate frontiers of physics. Here, density may exceed that of atomic nuclei by 5 to 10-fold, while temperatures could soar to billions of degrees Celsius. Under such extreme conditions, forever beyond the reach of human laboratories, even fundamental particles like neutrons may fail to maintain their integrity. Matter may undergo its final fundamental phase transition, from a state composed of neutrons to an ocean formed by even more fundamental particles, quarks. This is what theoretical physicists hypothesize as quark matter, a bizarre state of matter known as quark soup. According to the standard model of particle physics, hadrons like protons and neutrons are not fundamental particles. They are bound together by the strong force from even more fundamental quarks. Under normal conditions, quarks are permanently confined within hadrons. This phenomenon is known as quark confinement. You can never isolate a single quark. But within the core of a neutron star, the unimaginably immense pressure may hold the only key. capable of shattering the cage of quark confinement. When density reaches a certain threshold, neutrons in adjacent atomic nuclei overlap, their boundaries blurring. They may disintegrate entirely, releasing their internal up and down quarks, to form a plasma composed of free quarks and gluons. This is the envisioned landscape of quark soup. Gluons are the messenger particles that mediate the strong force. Within this fiery, dense soup, quarks and gluons can flow almost freely. This state of matter is thought to recreate the primordial universe, as it existed mere millionths of a second after the Big Bang. When the core of a neutron star exhibits this state, it becomes a bridge connecting the universe's beginning and end, an ancient relic existing within our present cosmos. Things may be even stranger. A widely discussed theory suggests that within this extreme quark matter, peculiar S-quark, or strange quark, could be produced in large quantities. S-quarks are heavier than the up and down quarks that make up ordinary matter, and typically appear only fleetingly in high-energy collisions. Yet within the stable, high-pressure environment of a neutron star core, they could become stable and abundant. Matter composed of nearly equal quantities of up quarks, down quarks, and strange quarks is termed strange matter. Hypotheses suggest this strange matter might represent the most stable form of matter in the truest sense, outstripping the stability of the proton-neutron matter common in our universe. If this hypothesis holds true, then the entire core of a neutron star, or even the neutron star itself, could be a massive strange quark planet, whose physical properties would exhibit subtle yet critical differences from standard neutron stars. However, distinguishing a standard neutron star from a strange quark star through external observation remains one of the most challenging frontiers in contemporary astrophysics. Another postulated marvel does not occur beneath the crust, but may exist within this transitional core region, near the phase boundary between ordinary nuclear matter and quark matter, where matter could organize into various regular geometric shapes. These structures are collectively termed nuclear pasta by physicists, yet they are more peculiar than those found in the crust. Here, alternating layers of quark matter and nuclear matter may form. For instance, quark matter could form minute droplets, embedded within a background of nuclear matter, termed nucleon puffs, or conversely, nuclear matter might form droplets suspended within an ocean of quark matter, known as quark puffs. As density increases toward the core, these shapes could further evolve into more ordered layered or tubular structures, referred to as quark lasagna and quark noodles. These structures would be periodically arranged on the microscopic scale, forming a crystalline arrangement unprecedented in the cosmos. The existence of these exotic material forms would significantly impact the overall properties of neutron stars. For instance, a neutron star containing a quark core might have a lower maximum mass than one composed solely of neutron matter, and potentially a smaller radius. This directly influences how we infer the internal structure of neutron stars. To infer the internal structure of neutron stars, when two neutron stars merge, if a quark core exists within them, the fate of the residual object formed after merger, and the abundance of heavy elements ejected, will differ from predictions of the Standard Model. The quest for quark cores and exotic matter is not merely to satisfy our curiosity about the universe. It directly relates to our understanding of the fundamental interactions in nature. Quantum chromodynamics is the theory describing the strong interaction, but in regions of high density and low temperature, its calculations become extraordinarily complex. The neutron star core provides a natural laboratory to test these theoretical calculations. Though we cannot directly observe the interior of neutron stars, by combining observations from multi-messenger astronomy, including radio pulsar timing, X-ray and gamma-ray observations, and gravitational wave astronomy data. We are painting an internal portrait of this most extreme cosmic object. In unprecedented detail, each periodic flash of a pulsar, each burst of X-rays, and each ripple in space-time may hold the key to unlocking its core secrets. The fantastical journey into neutron stars has now reached the known frontier. Beyond lies the uncharted territory on physics' map. This unknown realm has inspired generations of scientists to propose new theories and devise novel observational methods, all to answer that ultimate question. Under gravity's ultimate pressure, what form will matter ultimately take? The answer lies locked within the densest stellar cores in the universe. Neutron stars are not silent, cold stellar corpses. They are highly active, dynamic celestial bodies. One of their most striking features is their astonishingly rapid spin. Newborn neutron stars inherit angular momentum from the collapsing core of a massive star. Due to the conservation of angular momentum, when a massive stellar core shrinks dramatically from a size equivalent to a city to just 20 kilometers in diameter, its rotational speed increases dramatically, much like a figure skater spinning faster by pulling their arms in. This process is a cosmic scale amplification of the skater's spin effect. The result is the universe's fastest natural gyroscope. Some young neutron stars spin hundreds of times per second, with the highest recorded rate approaching 1,000 revolutions per second. This means a point on its equator could move at speeds reaching 1/10 the speed of light or higher, nearly reaching the rotational limit permitted by general relativity. Any faster, an immense centrifugal force would tear the star apart. This extreme rotation produces numerous peculiar physical effects. Centrifugal force distorts the neutron star's shape from a perfect sphere to a slightly bulging equatorial region, forming an extremely small oblate spheroid, though its surface gravity is immense and would crush any mountain range. This overall deformation caused by rapid rotation is undeniably real. If this minute deformation were frozen within the stellar structure, it would create a persistent asymmetric mass distribution. A rotating asymmetrical mass continuously emits gravitational waves. These gravitational waves carry away the system's energy and angular momentum, gradually slowing the neutron star's rotation. For certain binary systems, this gravitational wave emission is even the dominant mechanism driving orbital evolution. Many of these rapidly spinning neutron stars manifest as pulsars, continuously emitting narrow beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, this radiation beam sweeps across space like a cosmic lighthouse. If Earth happens to lie along the path of this radiation beam, we can detect extremely stable periodic pulse signals. The pulse period directly corresponds to the neutron star's rotation period. The first pulsar discovered by humans, CP1919, has a pulse period of 1.337 seconds. This means the star completes nearly 1 rotation per second. Later discovered millisecond pulsars exhibit rotation periods as short as 1.4 milliseconds, spinning over 700 times per second, with timing precision surpassing Earth's atomic clocks. These millisecond pulsars are considered recycled pulsars, acquiring additional angular momentum by accreting matter from their binary companions, gaining additional angular momentum to accelerate to astonishing rotational speeds. They function as the universe's most precise timekeepers, providing astronomers with unique tools to test gravitational theories, detect gravitational waves, and even search for exoplanets. Neutron star rotation is not eternal. The vast majority of pulsars experience extremely gradual deceleration, with their primary energy loss channel being the dissipation of magnetic dipole radiation through their powerful magnetic fields. This deceleration is typically very stable, but is occasionally interrupted by a phenomenon called a spin-up event, where the star's rotational speed suddenly increases slightly. This is usually interpreted as a sudden change in the coupling state between superfluid vortices and the solid crust within the star, or as a starquake, causing an instantaneous reduction in the star's moment of inertia, thereby accelerating its rotation. This cosmic blender, spinning hundreds of times per second, demonstrates the ultimate power of angular momentum conservation. With its precise rhythm and ferocious velocity, it stands as proof that stars refuse to fade into silence after death, and serves as the universe's singular timekeeping standard. If a neutron star's rapid rotation is astonishing, then its super-strong magnetic field reigns supreme as the magnetic king of the cosmos. The surface magnetic field strength of a typical neutron star can reach 10 to 10 teslas. This is 1 trillion to 10 trillion times stronger than Earth's magnetic field. Earth's magnetic field strength is approximately 0.00005 teslas. A common refrigerator magnet generates about 0.01 teslas. Even the strongest medical MRI machines only generate a few teslas. The magnetic field strength of neutron stars completely surpasses any experience in the human world. Such a powerful magnetic field does not arise from nothing. It is partially inherited from its progenitor star. During the process of stellar core collapse forming a neutron star, the star's original magnetic field lines are extremely compressed and frozen within the ionized matter. As the star's radius shrinks dramatically, its magnetic field strength intensifies dramatically, with the increase roughly inversely proportional to the square of the radius. When the radius shrinks by a factor of 100,000, the magnetic field strength could theoretically increase by a factor of 10 billion. Additionally, theories suggest a potential generator mechanism may exist within neutron stars, such as convective motion within their superfluid core, which could further amplify and sustain this extraordinary magnetic field. The neutron star's powerful magnetic field dominates its surrounding space environment, forming a complex magnetosphere. Within this magnetosphere, the motion of charged particles is entirely constrained by the magnetic field, spiraling along magnetic field lines, and confined to specific regions. The magnetosphere does not extend infinitely, but encounters a light-speed cylinder at a certain distance, corrotating with the star at the same angular velocity. Beyond this boundary, the corrotation speed would exceed the speed of light, which is physically impossible. Thus, the magnetosphere structure becomes highly complex at this point, serving as the key region for radiation generation. Such an immense magnetic field possesses astonishing, long-range destructive power. A frequently cited example is, if you carry a credit card at a distance of 100,000 kilometers from a typical neutron star, or even farther, its powerful magnetic field is sufficient to instantly demagnetize the card's magnetic strip, rendering it completely useless. Yet this represents only a minuscule fraction of its power. At closer distances, its magnetic intensity can distort the electron cloud structure of atoms themselves, altering the chemical properties of matter, and even stretching atoms into elongated cylindrical shapes. All matter subjected to such extreme magnetic fields exhibits profoundly bizarre characteristics. For instance, photon propagation in this environment undergoes splitting, producing the so-called vacuum birefringence effect. This resembles light passing through a crystal with extreme birefringence. For a class of neutron stars possessing exceptionally strong magnetic fields, we refer to them as magnetars. Their magnetic field strength can reach up to 10 to the power of 11 Tesla, over 1,000 times stronger than ordinary neutron stars. They are the celestial bodies with the strongest known magnetic fields in the universe. The energy of magnetars primarily does not stem from the dissipation of rotational kinetic energy, but from the decay and reorganization of their super-strong magnetic fields. They intermittently release enormous amounts of energy in the form of violent X-ray and gamma-ray bursts, known as soft gamma-ray repeaters. A single such burst, lasting just 0.1 seconds, can release more energy than the sun emits over 100,000 years. Its power is sufficient to influence the cosmic environment within thousands of light years. The magnetic field of a neutron star is not eternal either. It slowly decays over time. Magnetars may represent a brief yet intense phase in the life of a young neutron star. Before its magnetic field significantly weakens, their powerful magnetic fields serve as the core engine, driving the diverse high-energy radiation phenomena we observe, to the violent gamma-ray bursts of magnetars. All trace their energy origins to this most extreme magnetic field in the cosmos. Like an invisible giant hand, it holds the ultimate key to particle acceleration and energy release. As one of the most dynamic objects in the universe, a neutron star's behavior extends beyond rapid rotation and powerful magnetism, but also encompass a more violent energy release process. Starquakes. Starquakes, as the name suggests, are seismic events occurring on neutron stars. Yet their scale and released energy far exceed those of earthquakes by billions of times. Their origin lies in the neutron star's own structure under extreme physical conditions. The solid crust of a neutron star is composed of the hardest material in the universe. This substance, known as nuclear spaghetti, though extremely strong, is not unchangeable. As the neutron star's rotation gradually slows, its centrifugal force diminishes, causing minute adjustments to the star's shape, shifting from a slightly flattened sphere toward a more perfect sphere. This process imposes continuous stress on the rigid crust. Meanwhile, electromagnetic coupling between the superfluid vortices within the neutron star and the crust generates additional torque. These factors collectively cause stress to accumulate deep within the crust, like rock being slowly compressed. When this stress builds beyond the material's tolerance limit, the entire crustal structure undergoes sudden, global fractures and slippage. This is a stellar quake. The energy released during a stellar quake is astronomical, sufficient to instantly alter the entire star's rotational state. We observe many pulsars exhibiting a phenomenon called spin flip, where their extremely stable rotation periods suddenly shorten slightly, before gradually returning to their previous trend over the following days to months. This is one of the most direct observational evidences of starquakes. When the crust fractures and reorganizes, the celestial body's moment of inertia instantly decreases. According to the conservation of angular momentum, its rotational speed suddenly accelerates. This is analogous to a spinning figure skater abruptly pulling in their outstretched arms, causing the rotation to accelerate sharply. Subsequently, the interaction between the internal superfluid and the crust gradually relaxes the rotational speed back to pre-quake levels. The energy released by a starquake extends far beyond adjusting rotation. It also triggers violent reorganization of the magnetosphere. The powerful magnetic field lines of neutron stars are frozen within the conductive stellar core. When the crust undergoes massive displacement, these magnetic field lines are dragged along, causing the magnetic structure to undergo drastic changes in a short time. This process of magnetic reconnection releases enormous energy, accelerating surrounding charged particles to near light speeds, and generating intense electromagnetic radiation spanning from radio to gamma-ray wavelengths. For a specific class of neutron stars with exceptionally strong magnetic fields, magnetars, starquakes serve as the key mechanism triggering their massive energy explosions. The magnetic fields of magnetars are so intense that their stored energy reserves are unimaginably vast. A single starquake can unleash this colossal magnetic energy reserve, triggering massive X-ray and gamma-ray bursts, lasting from tenths of a second to several minutes. Such events are known as soft gamma-ray repeaters. The gamma-ray energy released in a single such burst may exceed the total energy emitted by the Sun over hundreds of thousands of years. Its power is sufficient to influence the cosmic environment within thousands of light years. If such an explosion occurred in a star system sufficiently close to us, could even cause devastating effects on planetary atmospheres. Beyond the spectacular electromagnetic radiation display of this energy release, starquakes exert another more subtle yet profound influence. By stirring ripples in spacetime, gravitational waves. Any change in the distribution of non-spherically symmetric mass generates gravitational waves. A violent, global-scale crustal realignment undoubtedly constitutes a massive redistribution of mass that produces detectable fluctuations in the fabric of spacetime. Though the gravitational wave signal from a single starquake may be faint, it represents a potential mechanism for continuous gravitational wave sources. As the sensitivity of gravitational wave detectors continues to improve, we may one day directly hear the spacetime tremors triggered by these cosmic quakes. When neutron stars in a binary system ultimately merge, their energy release reaches its zenith. The two neutron stars orbit each other, spiraling closer until they violently collide. This process unleashes immense energy in three distinct forms. First, in the instant before merger, their powerful gravitational fields violently distort spacetime in the form of gravitational waves, releasing energy far exceeding that of a single stellar shock. These gravitational wave signals have been successfully detected by human detectors such as LIGO and Virgo. Second, at the moment of merger, the violent collision ejects a small amount of neutron-rich material. Within this material, rapid neutron capture processes, rapidly synthesizing heavy elements like gold, silver, and platinum, accompanied by a brief electromagnetic radiation burst, known as a kilonova event, whose brightness can exceed that of a nova by 1,000-fold. Finally, the remnant celestial body formed after merger, whether a massive neutron star or a black hole formed by instantaneous collapse, may point its intense activity in another direction, producing an extremely short-lived yet highly energetic gamma-ray burst. Short gamma-ray bursts, their energy source is believed to be relativistic jets generated as the post-merger black hole accretes surrounding matter. When these jets happen to align with Earth's direction, we detect the final cry of this cosmic catastrophe. From a tiny crack in a star's crust to a cosmic-scale explosion triggered by binary merger, neutron stars profoundly shape their cosmic environment. Through these dynamic energy releases, profoundly shape their cosmic surroundings. They embody not only the ultimate extremes of gravity and density, but also serve as indispensable cosmic energy engines and element factories. Every tremor of stellar quakes, every realignment of magnetic fields, every roar of mergers, narrates to us the eternal and magnificent symphony of destruction and creation within this universe. In the profound darkness of the cosmos, a celestial body with unparalleled regularity continually sends precise signals to Earth. This is the pulsar, the most representative and widely known member of the neutron star family. At its core, A pulsar is a rapidly spinning magnetized neutron star. Yet the key to its detectability by us lies in a unique radiation mechanism, the cosmic lighthouse effect. To grasp this phenomenon, we must visualize the physical landscape of a neutron star's magnetosphere. Neutron stars possess intensely strong dipole magnetic fields. Their magnetic poles typically do not align with their rotational axis, instead forming an angle. In the regions near the magnetic poles, powerful electric and magnetic fields extract charged particles, primarily electrons and positrons, from the stellar surface and accelerate them to near-light speeds. As these high-energy particles travel along curved magnetic field lines, they emit highly directional radiation, known as curvature radiation or synchrotron radiation, whose energy range extends from the radio band all the way to the gamma-ray band. Crucially, this radiation is not emitted uniformly in all directions. Instead, it is beamed out from the polar regions in two narrow conical beams. Like two highly focused searchlights in the cosmos, these beams sweep across the universe as the neutron star spins rapidly. If Earth happens to lie in the path of one of these beams, we periodically detect a brief pulse signal. This is akin to observing a distant lighthouse, where we see a single flash only when its beam momentarily sweeps across our line of sight. Each rotation of the neutron star results in one or two recorded pulses, depending on whether one or both beams are sweeping past Earth. This phenomenon gave pulsars their name. This lighthouse model perfectly explains the most fundamental observational characteristic of pulsars: exceptionally stable pulse periods. The pulse period of a pulsar corresponds to the neutron star's rotation period. Its stability rivals that of Earth's most precise atomic clocks. Certain millisecond pulsars, monitored over decades, exhibit remarkably small variations in their period rate. This unparalleled timing stability makes pulsars unique tools for astronomers to test physical laws. For instance, by monitoring pulse arrival time variations in binary pulsar systems, we can test general relativity's predictions with unprecedented precision, and indirectly confirm the existence of gravitational waves. The pulse shapes emitted by different pulsars also vary greatly. Some are simple and sharp. Others are complex with multiple subcomponents. This reflects each pulsar's unique magnetospheric geometry. The observed pulse contours are actually images captured as our line of sight traverses different cross-sections of their radiation cone. Pulsar radiation is not constant. Occasionally, a phenomenon called pulse nulling occurs, where the pulse signal abruptly vanishes for a period, before reappearing. This may result from temporary reorganization of their magnetospheric structure, temporarily deflecting the radiation beam away from Earth. Although pulsars were initially discovered in the radio wavelength band, we now know they emit radiation across the entire electromagnetic spectrum, from radio and optical to X-rays and gamma rays. Some pulsars may even possess detectable signals in non-electromagnetic domains, such as high-energy cosmic rays and neutrinos. This cosmic lighthouse, with its precise rhythm and directional beam, not only reveals the physical mysteries of neutron stars themselves, but also serves as an invaluable tool for exploring the profound spacetime of the universe. The discovery of pulsars by humanity stands as one of the most dramatic chapters in scientific history. It began with an observation anomaly that seemed insignificant, yet ultimately opened a new gateway to the extreme physics of the cosmos. The year was 1967, at the Mullard Radio Astronomy Observatory of the University of Cambridge, UK. A graduate student named Jocelyn Bell was working under the guidance of Professor Anthony Hewish, using a new radio telescope to study the interstellar flickering of quasars. While analyzing kilometers of recorded data on paper tape, Bell noticed an unusual signal, a faint yet remarkably regular radio pulse, occurring every 1.337 seconds. The signal's periodicity was astonishingly stable, with precision reaching 1 part in 10 million, far exceeding the regularity achievable by any known natural phenomenon. This discovery immediately sparked profound confusion and excitement within the research team. After ruling out all possible artificial sources on Earth, a bold and thrilling idea emerged. Could this be a signal from extraterrestrial intelligent life? They jokingly dubbed the source Little Green Man 1, imagining it as an interstellar navigation beacon established by an advanced alien civilization, or perhaps an attempt to communicate with us. Over the following months, Bell continued analyzing the vast data with astonishing perseverance and meticulousness. Continued analyzing the vast data sets. Fate once again revealed its magic. She soon discovered 3 more radio signal sources, with different periodicities but equally precise rhythms. These were distributed across different directions in the sky. This discovery instantly made the Little Green Man hypothesis highly improbable. It was difficult to imagine 4 independent extraterrestrial civilizations, coincidentally transmitting signals to Earth at similar times, using different frequencies. The truth finally came to light. What they had discovered was an entirely new type of natural celestial object, pulsar. Its essence was a rapidly rotating, magnetized neutron star. In February 1968, this discovery was formally published in Nature magazine, immediately causing a sensation throughout the global scientific community. It not only confirmed the real existence of neutron stars, these extreme celestial bodies, but also provided an unprecedentedly powerful tool for studying the late stages of stellar evolution and the state of dense matter. Anthony Hewish, for his decisive role in the pulsar discovery, was awarded the Nobel Prize in Physics in 1974, while Jocelyn Bell's contributions were not recognized by the Nobel Prize. Her keen observational skills and rigorous scientific approach earned her widespread acclaim and respect throughout the global scientific community. Her story has become a classic case study, exploring the relationship between scientific contributions and award recognition. Looking back at this history, CP1919, once suspected of being a Little Green Man signal, we now know it is a pulsar in the constellation Vulpecula, located approximately 2,000 light-years from us. Its signal did not originate from an extraterrestrial civilization, but rather a magnificent display of cosmic forces, a miracle shaped by the interplay of gravity and quantum mechanics. From that cold Cambridge night, humanity's vision of cosmic exploration was forever expanded. By this rhythmic sequence of ticks, we discovered not only a new type of celestial object, but also a new way to listen to the deep, rhythmic heartbeat of the universe. Many great discoveries in human scientific history often begin with keen insight into subtle anomalies. The discovery of pulsars stands as a classic example. Its story is inextricably linked to the persistence and rigor of a young female graduate student. In the mid-1960s, the University of Cambridge constructed a new radio telescope, aimed at studying the interstellar flickering phenomenon of quasars. This telescope comprised thousands of antennas and 200 kilometers of wiring, spanning an area equivalent to 57 tennis courts. Its design sensitivity was sufficient to detect faint, rapid signal variations. Professor Anthony Hewish, responsible for constructing the telescope, assigned his graduate student Jocelyn Bell the task of conducting daily observations and analyzing data. Bell had to meticulously examine kilometers of weekly recording tape to extract valuable scientific information. One afternoon in August 1967, Bell noticed an unusual signal while analyzing data. It was an anomaly about 1.2 centimeters long, standing out starkly against the long, monotonous curve of the recording. This signal appeared during observations at midnight, meaning it moved with the sidereal time, ruling out the possibility of artificial interference from Earth. With the characteristic rigor of a scientist, and scribbled the cryptic Scott note, along with a question mark. Over the following weeks, she and her team attempted to capture the signal using higher-resolution timekeeping instruments. Finally, on November 28th, they successfully recorded a series of extremely regular pulse signals, with a period of 1.337 seconds. Their stability reached 1 part in 10 million, far exceeding the regularity of any known natural phenomenon. This discovery left the research team both exhilarated and perplexed. After ruling out all possible artificial sources on Earth, they even contemplated the possibility of extraterrestrial intelligent life, half-jokingly naming the source Little Green Man 1. Yet science demands rigorous evidence. Bell continued to immerse herself in the vast datasets. Through her persistence and meticulousness, over the following months, she discovered 3 more signal sources with different periodicities but equally precise rhythms. This discovery completely ruled out the extraterrestrial hypothesis, as it was impossible for multiple distinct alien civilizations to simultaneously transmit signals to Earth in similar ways. February 1968. The discovery was formally published in Nature magazine, under the title Observations of a New Type of Radio Source. The paper introduced the term pulsar to describe this novel periodic radio source. The paper immediately caused a sensation in the astronomical community. It not only confirmed the existence of neutron stars, predicted theoretically over 30 years earlier, but more importantly, it revealed an entirely new astrophysical phenomenon that opened a new door for studying the state of matter under extreme physical conditions. In 1974, Anthony Hewish was awarded the Nobel Prize in Physics for his decisive role in the discovery of pulsars. However, the award did not include Jocelyn Bell. This omission sparked decades of widespread debate within the scientific community. Many prominent scientists publicly stated, Bell's contributions to the discovery deserved greater recognition. Despite missing out on the Nobel Prize, Bell's academic achievements earned worldwide respect. She later became a Fellow of the Royal Society, served as principal and dean at several prestigious universities. Her scientific spirit and the discovery itself continue to inspire countless young people to pursue scientific careers. Particularly, it encouraged more women to pursue their dreams in science. Reflecting on this history, the discovery of pulsars represents not only a milestone in astronomy, but also a vivid embodiment of scientific methodology. From meticulously observing anomalous phenomena to rigorously eliminating various possibilities, ultimately arriving at a revolutionary conclusion, this process perfectly illustrates the essence of scientific inquiry, and the name Jocelyn Bell will forever be linked to this monumental discovery. It reminds us that scientific progress often relies on researchers who uncover the extraordinary within ordinary data. After over half a century of continuous observation and research, our understanding of neutron star distribution and abundance in the universe has become significantly clearer. Current astronomical estimates suggest that within our own Milky Way galaxy, there may exist between 100 million and 1 billion neutron stars. This vast range reflects the challenges of detection, as the vast majority of neutron stars are not detected as pulsars. They may have ceased pulsing, or their radiation beams may not sweep past Earth, becoming silent travelers in the cosmos. Estimates of the total number of neutron stars in the Milky Way are primarily based on calculations of star formation rates and supernova explosion frequencies. Astronomers have observed that the Milky Way experiences 1 to 3 supernova explosions per century on average. Considering the galaxy's history spanning billions of years, even if only a small fraction of massive stars ultimately form neutron stars, the cumulative number would reach staggering proportions. These neutron stars are not uniformly distributed across the Milky Way. They are primarily concentrated in the galactic disk, particularly within the spiral arms, as these regions host the most active star formation. Massive stars have remarkably short lifespans, spanning only millions to tens of millions of years. They typically end their lives near their birthplaces, forming neutron stars. Some neutron stars gain immense recoil velocity during their supernova explosions, reaching hundreds of kilometers per second. These high-velocity neutron stars are termed runaway neutron stars. They escape their birthplaces to wander the Milky Way in isolation. Our primary method for detecting neutron stars is through the periodic signals they emit as pulsars. Astronomers have now discovered over 3,000 pulsars within the Milky Way, a number that continues to grow with the continuous advancement of radio telescope technology. These known pulsars can be classified into several major categories, based on their characteristics and environments. Most are ordinary radio pulsars, with periods ranging from 0.1 seconds to several seconds, primarily distributed across the galactic disk. Another particularly significant category comprises millisecond pulsars, with rotation periods ranging from 1 to 10 milliseconds. These are believed to form when aged neutron stars in binary systems reaccelerate through accretion of material from their companion stars. The rotation of these millisecond pulsars is exceptionally stable, making them ideal tools for studying gravitational waves and detecting exoplanets. Additionally, young pulsars associated with supernova remnants exist, such as the famous Crab Nebula pulsar and the Vela pulsar, which provide invaluable samples for studying the early evolution of neutron stars. Beyond isolated pulsars, there are pulsars within binary systems, some of which accrete material from their companions, emitting intense X-ray radiation, known as X-ray binaries. Research into neutron star populations within the Milky Way not only helps us understand the stellar life cycle, but also provides natural laboratories for exploring extreme physical conditions. Through these studies, we can test the applicability of physical laws in environments of intense gravitational fields and superstrong magnetic fields, understand the behavior of matter at nuclear densities, and even explore clues to quantum gravity. With the deployment of next-generation radio telescopes like China's FAST and the Square Kilometre Array, we will discover more faint, distant neutron stars, further enriching our knowledge of these cosmic extremes. The silent presence of hundreds of millions of neutron stars in the Milky Way reminds us of the vastness of the universe and the diversity of nature. They are the inevitable products of stellar evolution and crucial links in the cosmic cycle of matter. Each one narrates the magnificent epic of stellar birth and death. In the grand narrative of the cosmos, neutron stars play a role far more significant than we could ever imagine. They are not only masterpieces of gravity and stellar remnants, but also the forges of heavy elements in the universe. To understand this process, we must turn our gaze to a special type of system, binary neutron star systems. When two massive stars are born as a binary system, their fates become inextricably linked. If both stars possess sufficient mass, they will successively undergo supernova explosions, each leaving behind a neutron star. These two dense celestial bodies, bound by gravity, continue to orbit each other, forming an extremely compact binary system. Such a system is not static. According to Einstein's general relativity, any massive object undergoing accelerated motion radiates energy in the form of gravitational waves. Two compact neutron stars orbiting closely together constitute a powerful gravitational wave source. Gravitational waves are ripples in the fabric of spacetime. They propagate at the speed of light, carrying energy across the cosmos. Within a binary neutron star system, the emission of gravitational waves continuously drains the system's orbital energy, causing the orbital energy of the two neutron stars to gradually diminish. They spiral closer to each other, rotating faster and faster, with increasingly shorter orbital periods. This process can persist for millions of years or longer, until the two stars ultimately merge. Observational studies of binary neutron star systems have significantly advanced fundamental physics. The most famous example is PSR B 1913+16, discovered by Hulse and Taylor in 1974. This marked humanity's first discovery of a binary neutron star system. Through decades of precise monitoring, scientists observed its orbital period gradually shortening, exactly matching the prediction of general relativity, that gravitational wave radiation causes energy loss. This provided the first indirect evidence for gravitational waves, and earned Hulse and Taylor the 1993 Nobel Prize in Physics. Another milestone was the 2017 detection of the binary neutron star merger GW 170817. This marked humanity's first cosmic event, observed simultaneously through gravitational waves and electromagnetic radiation, signaling the dawn of a new era in multi-messenger astronomy. During the prolonged evolution of binary systems, if one component is a neutron star, while the other is an ordinary star, the dynamics differ significantly. The neutron star's intense gravity strips material from its companion star's surface. This material forms a rotating accretion disk that eventually falls onto the neutron star's surface. This process emits intense X-rays, making the system an X-ray binary. Simultaneously, the accreted material transfers angular momentum, accelerating the neutron star's rotation to form a millisecond pulsar. These reborn pulsars become the most precise clocks in the universe. The existence and evolution of binary neutron star systems demonstrate extreme forms of matter interaction in the cosmos. They serve not only as natural laboratories for testing gravitational theories, but also as pivotal sites for the origin of heavy elements in the universe. By studying these cosmic duets, we gain insights into matter's behavior under extreme conditions, understand the evolutionary history of the universe, and even trace the origins of the elements that make up our very existence. Driven by gravitational waves, after prolonged orbital decay, the binary neutron stars meet their ultimate fate, merging. This process ranks among the most violent events in the cosmos, its spectacle rivaled only by supernova explosions and black hole mergers. In the final moments before merger, the two neutron stars orbit each other at astonishing speeds, reaching hundreds of revolutions per second. Their distance shrinks to mere tens of kilometers. Almost touching, powerful tidal forces begin significantly warping the stars' shapes, stretching them into teardrop forms, stripping away small amounts of material from their surfaces, and flinging it into surrounding space. The final moment is violent and swift. The two stars collide at extreme velocity. This collision velocity can reach 1/3 the speed of light. The resulting shockwave propagates through the stars. Temperatures instantly soar to hundreds of billions of degrees. Densities exceed those of atomic nuclei. Under such extreme conditions, the fundamental nature of matter undergoes a radical transformation. Neutron star matter may be broken down into its basic constituents, quarks and gluons, forming a fleeting quark-gluon plasma. This state of matter resembles the universe's condition during the first microseconds after the Big Bang. This provides a unique window into the study of the early universe. The outcome of the collision depends on the total mass of the two neutron stars. If the combined mass is less than approximately 3 solar masses, the merger may form a massive neutron star. Although this newborn may only exist for a brief period, it will eventually collapse into a black hole due to instability. If the total mass is higher, they may collapse directly into a black hole. During the merger process, a small fraction of material, roughly a few percent of the solar mass, is ejected into interstellar space at speeds approaching the speed of light. These ejecta serve as key raw materials for cosmic alchemy. Rich in neutrons, they create ideal conditions for rapid neutron capture processes. In this process, atomic nuclei capture large numbers of neutrons within extremely short time frames and then transform via beta decay into heavier, stable elements. This process produces most of the universe's precious metals, including gold, silver, platinum, and radioactive elements like uranium and thorium. Merger events also emit intense electromagnetic radiation. Shortly after coalescence, decay of radioactive elements within the ejected material generates brilliant light spanning ultraviolet to near-infrared wavelengths. This phenomenon is termed a millisecond nova, which can reach 1,000 times the brightness of a nova, yet remains far dimmer than a supernova. The light curves and spectral characteristics of millenary novae provide direct observational evidence of element synthesis during merger processes. The merger of binary neutron stars is also the primary source of short gamma-ray bursts. When merging forms a black hole, a transient accretion disk may form around it. Near-light-speed jets are ejected from the black hole's poles. If the jet direction happens to be aligned with Earth, we observe a high-energy gamma-ray burst lasting several seconds. The GW170817 event, detected on August 17, 2017, perfectly demonstrated this complete picture. Following the gravitational wave signal, a short gamma-ray burst was detected in the same sky region. Subsequently, over the next days and weeks, observations spanning the full electromagnetic spectrum from X-rays to radio waves. Across the entire electromagnetic spectrum, these observations confirmed that binary neutron star mergers are indeed the primary cosmic sources of heavy elements. They also transformed long-theorized cosmic scenarios into scientifically validated observational facts. Each neutron star merger event functions as a cosmic element factory, converting simple elements into complex heavy ones. These elements ultimately integrate into new generations of stellar and planetary systems, providing the essential material foundation for life's emergence. The gold within our bodies, the gold jewelry we wear, may all trace back to ancient times, to some cosmic alchemy of neutron star mergers. Every element heavier than iron in the universe depends on extreme and rare environments for its birth. One of the most crucial mechanisms is the rapid neutron capture process, commonly known as the R process. This process occurs during neutron star mergers. Among the most violent cosmic explosions, at the instant of a binary neutron star merger, massive amounts of neutron-rich material are ejected into interstellar space. This material is extremely hot and densely packed, creating perfect conditions for neutron capture. Unlike the slow neutron capture within stars, the core of the R process lies in its rapid nature. Within mere seconds, atomic nuclei capture vast numbers of free neutrons at such a rapid pace that the nuclei lack time to undergo beta decay before rapidly increasing in mass to form extremely unstable neutron-rich heavy nuclei. Only after this rapid mass gain phase concludes do these unstable heavy nuclei undergo a series of beta decays, converting internal neutrons into protons, thereby stabilizing and forming the heavy elements we recognize: gold, platinum, uranium, and others. This process resembles an intense race, where atomic nuclei must frantically capture as many neutrons as possible before stabilizing through decay. A gold nucleus requires capturing nearly 200 neutrons to transform from its initial iron nucleus. The environment provided by neutron star mergers is the only known place meeting all the stringent conditions of the R process: extremely high neutron density, extremely high temperature, and extremely rapid expansion and cooling rates. Each such merger event forges precious metals equivalent to several Earth masses and scatters them across the vast interstellar medium. These newly synthesized heavy elements mix with interstellar gas and dust to become the raw material for the next generation of stars and planetary systems. Our solar system, formed within such a gas cloud, contaminated by previous stars and neutron star mergers. Thus, all the heavy elements around us, from circuit boards in our phones to nuclear power plant fuel, can be traced back to a spectacular explosion event. In the cosmic history of neutron star mergers, the universe's most pivotal alchemists, when you wear a gold ring on your finger, you wear not merely an ornament, but a cosmic history spanning billions of years. The origin of this precious metal traces back to before Earth's formation, and even before the birth of our solar system. In the distant past, two neutron stars in a corner of the Milky Way performed a spectacular dance of death. Orbiting each other, they sent ripples through space-time until they collided violently. In this cosmic alchemy, vast quantities of gold were forged and hurled into space at near light speeds. These newborn gold atoms drifted through the interstellar medium for millions of years, until approximately 4.6 billion years ago, when the interstellar gas cloud they inhabited began to collapse under gravity, forming our sun and the protoplanetary disk surrounding it. During planetary formation, heavier elements like gold and platinum gradually migrated toward the inner solar system, ultimately being absorbed mostly by Earth. Due to gold's chemically stable nature, it readily reacts with other elements. It was preserved through Earth's long geological evolution and enriched within the planet's interior and crust. Later, through volcanic activity and tectonic movements, some gold deposits were brought near the surface to become mineral resources accessible to humans. Thus, the gleaming gold ring in your hand likely originated from a neutron star merger event that occurred 5 or even 6 billion years ago. At that time, the solar system had not yet formed. Earth did not exist. Yet these atoms, forged by the most violent events in the cosmos, traversed vast space-time to ultimately become part of your personal history. This realization profoundly connects the macrocosm with our daily lives. Our bodies also contain these heavy elements. Though present in minute quantities, they are undeniably present, participating in the metabolism of life. In this sense, we are not only children of light elements like carbon, nitrogen, and oxygen, but also descendants of heavy elements such as gold, iodine, and uranium. our very existence, is inextricably linked to the most extreme and violent phenomena in the cosmos. Each time you gaze upon a piece of gold jewelry, consider its epic cosmic journey, beginning with the remnants of two dense stars orbiting each other, enduring violent collisions and explosions, a long drift through interstellar space, before finally becoming part of a planet and being crafted into exquisite art by intelligent beings. This is an epic greater than any myth, and each of us is both witness and inheritor of this saga. As the story of neutron stars unfolds, we gradually recognize it is no one-dimensional cosmic wonder, but bears multiple identities, each revealing an extreme facet of the universe's operating principles. First, the neutron star stands as a monument to gravity's ultimate triumph. Gravity, the most fundamental and pervasive force in the cosmos, maintains a delicate equilibrium with outward radiation pressure throughout a star's long life. But when the nuclear fire at a star's core extinguishes and radiation pressure vanishes abruptly, gravity bears its purest fangs. Unopposed by any effective resistance, it unleashes a crushing, catastrophic gravitational collapse. It mercilessly compresses a mass larger than the Sun into a city-sized volume. This compression is so absolute that it destroys the fundamental structure upon which matter relies for existence. Atoms are forcibly compressed, with electrons forced into the nucleus to fuse with protons, forming neutrons. The entire star transforms into a gigantic atomic nucleus. This represents the critical state to which gravity can compress matter, the ultimate form matter can attain before becoming a black hole. It stands at the edge of the black hole's event horizon, demonstrating gravity's near-ultimate authority. Secondly, the neutron star embodies the extreme state of compressed matter, a unique natural laboratory of extreme physics in the cosmos. Within this laboratory, the state of matter surpasses any limits achievable in artificial environments on Earth, with internal densities reaching hundreds of millions of tons per cubic centimeter. This extreme density gives rise to material states unimaginable on Earth, from an indestructible iron crystal crust to a ghostly, frictionless neutron superfluid flowing within, to the deepest core where quark soup, composed of free quarks, may exist. These bizarre material states allow us to glimpse physical laws forever unobservable under normal conditions. The neutron star's super-strong magnetic field are 1 trillion times stronger than Earth's magnetic field. They provide the only available sample for studying the behavior of magnetohydrodynamics and quantum electrodynamics under extreme field conditions. Meanwhile, the immense gravitational pull at their surfaces allows us to test Einstein's general relativity with unprecedented precision. For instance, by monitoring pulsar binary systems orbiting around them, we can detect orbital decay caused by gravitational wave radiation, thereby indirectly confirming the existence of gravitational waves. All these extreme properties make neutron stars a touchstone for fundamental physics, constantly challenging and expanding the boundaries of our understanding of the material world. Furthermore, neutron stars are an indispensable key link in the cosmic cycle, perfectly embodying the profound dialectic relationship between death and rebirth, destruction and creation in the universe. They themselves are the product of a massive star's demise, a stellar gravestone, marking the end of a glorious life cycle. Yet, their birth process, the supernova explosion, scatters the heavy elements forged throughout the star's lifetime into interstellar space, sowing seeds for the formation of new generations of stars and planetary systems. More crucially, when neutron stars perform their final cosmic dance of death and violently collide, they act as the universe's ultimate alchemists, amidst the immense energy and abundant neutron flux generated by these mergers. Most of the universe's heavy elements, gold, silver, platinum, and others, are forged in an instant. These precious elements eventually merge into the nebulae that form new stars and planets. All the precious metals on our Earth and the trace heavy elements within our bodies may trace their origins back billions of years to one such neutron star merger event. Therefore, neutron stars are both the end of old life and the creators of new matter and new life. They profoundly participate in the cosmic cycle of matter, tightly linking the death of stars with the birth of life. In summary, neutron stars, with their multiple identities, have become a core piece of the puzzle in understanding how the universe operates. They are not only the battleground where gravity and quantum mechanics struggle under extreme conditions, but also a cosmic bridge linking stellar birth and death to the origins of life. By studying neutron stars, we not only resolve questions about stellar fates, but also trace the origins of the matter that forms our own world. They profoundly remind us of an ancient and fundamental connection between ourselves and these most violent, extreme objects in the cosmos.